We'll start the session. Good afternoon, everyone. I, Dr. Ganesh Archate, welcome for session 11, day 6. It is my pleasure to introduce our distinguished guest speaker, Sagitha Paroly. She has an interdisciplinary research background at the interface of chemistry and material science and have extensive research experience in fabrication, functionalization, and characterization of different functional materials for biomedical and environmental remediation applications. So she's working as a research and development scientist at Hexlattice Materials Private Limited, Karnataka. She's tailoring the applications of graphene and graphene derivatives. Earlier, she was a principal research scientist with Cell and Tissue Engineering Laboratory, Department of Bioscience and Bioengineering, IIT Bombay, where she was developing multifunctional biocompatible ionic liquids for DNA binding and drug solubilization. Before that, she was a content writer in chemistry with Sri Narayana Guru Open University, Kollam, Kerala. Contributed for developing academic book chapters for BSc Chemistry curriculum. She has done her PhD from NIT Calicut, MPhil in Chemistry from the University of Calicut, Kerala, and MSc in Applied Chemistry from Cochin University of Science and Technology, and BSc in Chemistry from Government Arts and Science College, University of Calicut, Kozhikode. She had won many prizes and awards. Among that, a few are 3 minutes thesis presentation on PU-based electrospun fibrous membranes for biomedical applications. National Conference, School of Material Science and Engineering at National Institute of Technology, Calicut, Kerala. And also she bagged Best Oral Presentation Award. And she is qualified in the GATE examination in chemistry. She has around 13 journal publications. So other public engagement activities, like she has been with laboratory experimentation demonstration for various events at NIT Calicut, Kerala, and she was invited for a lecture on an overview on electrospun membrane types, fabrication and applications in connection with a seminar that was conducted by the Department of Chemistry in Government Arts and Science College, Kozhikode, Kerala. Ma'am, forward to your session. Thank you.
Thank you, sir. Thank you for the introduction. So I'll share my screen. Hope my screen is visible.
Yes, it is visible.
Yeah. So first of all, many thanks for the ATAL Academy sponsored 1 week faculty development program organizers for inviting me to deliver a talk on the topic nanostructured functional materials and self-healing materials. So I'll try to give you an outline about what is made by nanostructured functional materials, especially about graphene and MXene, and also about the different types of self-healing materials. So let's start. We know that there are different types of materials in this nature, and these materials will be having different types of shape, structure, morphology, different applications, etc. So today what we are going to do is we are going to deal with a special kind of materials, which is known as nanomaterials. So nanomaterials are those materials which is having dimension, at least one of its dimension in the nanometer range. And those technology which is actually dealing with the nanomaterials are known as nanotechnology. So nanotechnology is an emerging area of research which is actually dealing with the nanomaterials, its synthesis, its functionalization, application, etc. And it's a very emerging field in research. And just one second. Okay, so it's an emerging field in research which is having applications in wide areas like biomedical, environmental remediation, and electronic applications, etc. So I'll try to give you an outline about the different types of nanomaterials, its applications, how it can be synthesized, everything. So already I told that there are different varieties of nanomaterials in this nature, and we can classify those nanomaterials into 3 categories. One is the inorganic nanomaterials, then organic nanomaterials, and carbon-based nanomaterials. Let's go to this topic one by one. So I'm going to talk about inorganic nanoparticles first. So inorganic nanomaterials may be the simplest kind of nanomaterials when we are comparing the three groups, the carbon based or organic based. So we can say like these are actually metal based nanomaterials or some ceramic based nanomaterials. Say for example, gold nanomaterial, silver nanomaterial, copper nanomaterials. These are like metal based nanomaterials, and there are some metal oxides based nanomaterials like iron oxide based nanomaterials, or there is like some titanium oxide based nanomaterials and silica based nanomaterials. These are comparatively small nanomaterials. These are mainly using for different types of biomedical applications and also about for electronic applications, etc. So, for example, if I am taking silver nanoparticle have the peculiarity like it is antibacterial in nature, so we can use it for different types of biomedical applications, especially for antibacterial property applications. And when we are trying to prepare nanomaterials, say for example, if we are trying to prepare silver nanomaterials, we can take a suitable precursor material and we can undergo some kind of reduction process to that, and we can make the respective nanomaterials. For silver nanoparticles, we can take silver nitrate as the precursor material, and it's very common to synthesize silver nanoparticle and very easy for preparation as well. We can do it in laboratory very easily. And these nanomaterials have their peculiar properties like high surface area to volume ratio. Because of their high surface area to volume ratio, nanoparticles are generally recommended in very small quantities compared to their bulk counterparts. And next category of nanomaterials are the organic nanomaterials. Unless the normal organic nanomaterials are generally made up of, they will be like carbohydrate based or dendrimers, liposomes, micelles, or ferritin based nanomaterials. And when we compare with other carbon based or inorganic nanomaterials, organic nanomaterials are generally biodegradable and they will be non toxic as well. So now I'm moving on to carbon-based nanoparticles. Carbon-based nanoparticles are very important category of nanoparticles in which wide range of research is going on. And this carbon-based nanomaterials are those nanomaterials which is having a carbon skeleton. And this carbon-based nanomaterials are emerging as a efficient tool in nanotechnology because of their remarkable mechanical, electrical, optical, and thermal properties. And thus carbon-based nanomaterials are widely using for different types of electronic applications, energy applications, healthcare applications, and water filtration or air filtration, that kind of environmental application as well. So let's move on to carbon-based nanoparticles more detail. There are different types of carbon-based nanoparticles, as you can see in the figure. There are nanoparticles like quantum dots are there, fullerenes are there, nanotubes are there, nanohorns are there, nanosheets are there, nanolayers are there. These are all like carbon-based nanoparticles. Their main structure or the skeletal structure will be like a carbon unit. And these nanoparticles we can classify into zero-dimensional, one-dimensional, or two-dimensional, or three-dimensional based upon how their dimensionality. So when we talk about one-dimensional, two-dimensional, or three-dimensional, it will be okay. But when we are talking about zero-dimensional, this term will be little bit confused. So because we will be thinking like, is it possible to have materials with zero dimension? So this, to avoid that confusion, I have kept a figure here. You can see that in this, I have represented the zero-dimensional material, one-dimensional material, and two-dimensional materials, carbon materials. As you can see in the figure, zero-dimensional materials are generally spherical in shape, and one-dimensional materials are generally rod-like or tubular in shape, and two-dimensional materials are generally planar in shape. So how the name 0, 1, and 2 came? So when we take the case of zero-dimensional spherical material, they are confined in the all three direct dimensions. That means they are confined in their x, y, z planar dimensions. They don't have any extensions in any of the dimension. Since they have no extension in any of the dimension, they are known as zero dimensional. And when we take the case of one-dimensional material, we can see that they are extended in one dimension. That's why they are known as the one-dimensional materials. In case of two-dimensional materials, they will be extended in two dimensions. That's why they are known as two-dimensional materials. So this let's talk about the zero-dimensional materials first. As I described, zero-dimensional materials are generally spherical in shape, and we usually represent it as carbon nanodots. Carbon nanodots are discovered in mid 2000s and they are very tiny. Usually they will have a dimension which is less than 10 nanometer. They will be spherical in shape and typically this carbon nanodots will be composed of carbon atoms. And along with the carbon atom, there will be some kind of doped kind of nanodots as well, nitrogen doped, oxygen or hydrogen doped nanodots also. And one of the important peculiarity of carbon nanodots is that they can provide bright fluorescence. When we talk about carbon based materials or carbon powder, nanopowder, or any other carbon based material, in our mind it will come like it's something like a black material. But the peculiarity of carbon nanodot among all other carbon based materials is that they can provide bright fluorescence. So they can provide bright fluorescence in the visible light range. So this is the photograph of the bright fluorescence the carbon dots can provide at different wavelengths in the visible region. So from this we can understand that the carbon nanodots are able to provide visible fluorescence in the bright visible region. And we can talk about the synthesis of carbon nanodots. There are different types of synthesis methods that we can adopt to prepare the carbon nanodots. This can be laser ablation techniques or electrochemical techniques or arc discharge techniques or ultrasonication based techniques or hydrothermal techniques or microwave pyrolysis techniques. We can categorize all these techniques into two groups. One is the top down approach and the other one is the bottom up approach. So as the name indicates, top down means we will take a carbon based precursor material and we will break it or chop down it into the small carbon dot units using laser ablation or electrochemical or arc discharge method. And in the bottom up approach, what we are doing is that we will take some organic molecules and we will perform carbonization of this material using some hydrothermal or microwave pyrolysis technique and producing the carbon dot. So when we compare the top down and bottom up approaches, what we are actually saying is that each method will have its own advantages and its own disadvantages as well. So when we compare top down and bottom up, we can say like top down approach is comparatively easy to perform rather than bottom up approaches. But one of the disadvantage of top down approach is that top down approach will not provide carbon dots with inherent bright fluorescence. In order to make the carbon dots which are produced by top down approach to fluorescent, we need to do some kind of post functionalization on their surface, and we will have to provide some additional polar functionalities on their surface to make it or to show bright fluorescence for the carbon dots. But those carbon dots which are produced using bottom up approach, we doesn't want to do any kind of post treatment to make it fluorescent. It will have the inherent fluorescent property. So we can say like bottom up approach as a one pot synthesis method for the carbon dots. And there are different types of carbon dots. Like there are carbon graphene based carbon dots and there are graphitic carbon dots. There are some amorphous kind of carbon dots and there are some doped carbon dots. So how this variety comes, it's based upon the precursor material that we are using to develop this kind of carbon dots. If you are using some graphene based precursor material for developing the quantum dots, it will give graphene based quantum dots. If you are using some graphitic precursor material for developing the quantum dots, it will provide graphitic quantum dots. And amorphous quantum dots are those type of quantum dots which will have some irregular kind of structures in it. And doped quantum dots are something like carbon nitride, which is shown here. It's something like nitrogen or oxygen or any other elements doped kind of carbon dots. So these are the different classifications of carbon dots. And since carbon dots are able to produce light bright fluorescence, it can be used for different types of optoelectronic applications. And the next category of the carbon-based nanomaterial, that is the carbon nanotube. As I discussed, this will come in the one-dimensional category. And in this case, it will, as the name indicates, it will be something like a tubular in shape. And some other case is like nanotubes as rods as well. Carbon nanotubes are discovered in 1991. They will be tubular in shape. As you can see in the structure, they are something like rolled graphene nanosheets. So tubes are formed by rolling graphene nanosheets. And graphene, I will discuss about the graphene in our later slides. So this is something like a rolled graphene sheet. And when we compare the length and dimension of carbon nanotubes, we can say like it will have a length in the micrometer range, and the diameter will be in the nanometer range. There are mainly two types of carbon nanotubes, that is the single walled carbon nanotubes and multi-walled carbon nanotubes. As the figure indicates, you can see that single walled carbon nanotubes will have only one wall. That means there will be only one tubular structure of the graphene sheet. But in case of multi-wall carbon nanotube, we can see that there is something like graphene stacked layers or tubes like stacked one over the other. So when we compare the diameter of single-walled and multi-walled carbon nanotubes, we can see that single-walled carbon nanotubes will have comparatively less diameter compared to the multi-walled carbon nanotubes. Single-walled nanotubes carbon nanotubes will have a diameter ranging from 0.5 to 2.5 nanometer, and for the multi-walled carbon nanotubes, their diameter will be ranging from 7 to 100 nanometer. Similarly, that of carbon nanodots, carbon nanotubes can also be prepared using different top-down and bottom-up approaches. Arc discharge, chemical vapor deposition, and laser ablation are the most commonly used methods for the synthesis of carbon nanotubes. And carbon nanotubes are also showing wide range of applications. One of the most important application of carbon nanotubes is that since it is having a tubular kind of arrangement of atoms in it, we can encapsulate drug molecules into the nanotubes, and we can use it for drug delivery applications. And also carbon nanotubes show some kind of antibacterial activity, so this can be used for antibacterial applications, and carbon nanotubes are using for sensing applications as well. This is one of the work which I have done, in which I am the co-author. We have developed polyurethane multi-walled carbon nanotube-based fibrous membranes for environmental remediation application. Here the application which we were specifically focusing was oil-water separation application. What we have done is that we developed a composite of polyurethane and multi-walled carbon nanotube in the form of a membrane using a technique which is known as electrospinning. So using this technique, we have developed the composite, and this represents the bonding interaction between carbon nanotubes and the polyurethane. So we can see like some kind of pi-pi stacking interaction between the carbon nanotube and the double bond in polyurethane structure. So why we developed this material? Because we know that polyurethane is a hydrophobic polymer. That means those kind of polymers which is having low affinity towards water. So our aim was to um, enhance the hydrophobicity of polyurethane. For that, we have used multi-walled carbon nanotubes as the filler material in the polymer. So when we have added the multi-walled carbon nanotube into the polyurethane matrix, it enhanced the hydrophobicity and it developed a super hydrophobic surface. So we could obtain super hydrophobic membrane using the functionalization with multi-walled carbon nanotube. And when we tried the when we tried the oil adsorption property of this membrane, what we have found is that this membrane could selectively remove oil particle from the oil-water mixture. So this petri dish is composed containing water and oil. Oil is recognized, or just to understand which is oil, we just made it with some color. And what we can see that when we try to wipe out the oil using our super adsorbing, super hydrophobic membrane, what we found is that it could absorb the oils selectively from the water mixture. And also we could see that it can separate oil water mixture, and we can get the oil and water separately using this membrane. So multi-wall carbon nanotubes can also be used for developing super hydrophobic surfaces. Now let me move on to the other category of carbon nanomaterial, which is the two-dimensional graphene and graphene derivatives, which is a very important category of the carbon-based nanomaterials. So in this category, we can discuss about graphite, graphene, graphene oxide, and reduced graphene oxide. When we are talking about this material, almost all material will have a similar property, similar structure, but some variations will be there, making them different from each other. So let me start from graphite. Graphite is a naturally occurring allotrope of carbon which forms by the reduction of sedimentary carbon during metamorphism. And graphite is having a structure like this. It is having a layered type of morphology in which each layer will be formed of carbon skeleton. So one layer of graphite, I can represent it here. So it is like only made up of carbon atom. The bold kind of structure which I have shown here is the carbon atom. You can see that the carbon atoms are arranged in a hexagonal type of lattice structure, and in which each carbon atom is sp2 hybridized. So this is the basic structure of one layer of a graphite. So many this kind of layers are stacked one over the other and forming the graphite layer. So this is the electronic arrangement or the layer arrangement in graphite. As you can see that each layers are joined by weak van der Waals forces of attraction, and between the layers the interlayer distance will be like in a nanometer range, mostly like 0.34 nanometer. So this is the basic structure of the layers in the graphite. So now let's move on to graphene. So when we are comparing graphite and graphene, what I can say that the individual layer in graphite is known as graphene. So we can say that graphite is a layer of many graphenes which are stacked one over the other. So individual layer is known as graphene. When we are comparing graphite and graphene, graphene will be more stronger than graphite. This is mainly because we can understand it using a simple example. As we all know, we all are using normal pencils, and the pencil lid is actually made up of a graphite. So when we are trying to write with the pencil, we know that we can easily write with the pencils. It's mainly because of its weak intermolecular attraction of the graphitic layers. So when we take the pencil lid, so we can see like there will be a large number of graphene layers in them. So when we are trying to write with the pencil, these layers are moving and the layers are getting separated. That's why we are able to write with that. Since this graphitic layers or graphene layers, in between the graphene layers, it is very weak van der Waals force of attraction. These layers can be easily separated. That's why we are able to write it with the graphite pencils. But in case of graphene is a single sheet of carbon structures. There is no intermolecular attraction or nothing like that. It is simply the carbon covalent bond between the carbon atoms. Covalent bonds are very strong. So when we take the single layer of graphene, it is stronger than graphite. And when we compare the electronic structure of carbon atom, we know that a carbon atom contains 4 electrons in their outermost shell, and it can form 4 bonds with the other molecules. But when we take the structure of graphene, if we are taking this carbon atom, you can see that this carbon atom is joined to 1, 2, 3 other carbon atoms. And if I am taking this carbon atom, you can see that it is joined to 1, 2, 3 other carbon atoms. So when you pick carbon atom from any end of this graphene sheet, you can see that each carbon atom are joined with 3 other carbon atoms. So obviously the fourth electron will be free. So this free electron, they are free to move throughout the structure because of this pi bonding delocalization. And since they are free to move, this is highly conductive as well. So graphene is highly conductive than graphite because graphite is something like a layered morphology. So their delocalization will get interrupted. But graphene is simply like one layer of structure, so that there won't be any disruption in their delocalization, so the electrons can be easily moved, and so making graphene more conductive than graphite. These are some peculiarities of a graphene. Graphene is the strongest material and it is the thinnest material ever discovered. And it is transparent and conductive as well. And it is having high fracture strength, high Young's modulus, high ampacity, large specific surface area, high thermal conductivity, and high light transmittance. Because of these properties, graphene is emerging as a very important nanomaterial or carbon-based material. As I said, graphene is very thin and we can make it is very mechanically strong as well, and the graphene is highly flexible as well. Because of this superior properties, graphene becomes the most promising material for various applications than graphite. So when we are looking into the structure of a graphene, it can be monolayer graphene or bilayer graphene or trilayer graphene. Since if it is monolayer graphene, it will have superior property compared to bilayer or trilayer graphene. As the number of graphene layer increases, it comes to the stage which is comes to the category which is graphite. So generally, when we are saying graphene, it should be like a monolayer or bilayer or trilayer or few layers. We can say like few layers. So we can say like there are monolayer graphenes, bilayer graphenes, trilayer graphenes, or few layer graphenes, or multi-layer graphenes, and then graphites like that. And there are different methods for the synthesis of a graphene, different top-down approaches and different bottom-up approaches. So these are the common top-down approaches of graphene synthesis: mechanical exfoliation, liquid phase exfoliation, electrochemical exfoliation. So these all we can classify as exfoliation techniques. And then reduction of graphitic oxide, that means graphene oxide, and arc discharge method. These are the common top-down approaches. Mainly, people are employing exfoliation techniques for the synthesis of graphene because it is most common and it's somewhat easy as well. And these are the some of the bottom-up approaches that we can use for developing graphene: chemical vapor deposition, laser-assisted synthesis, epitaxial growth, pyrolysis, organic synthesis, carbon monoxide reduction, etc. And among the different bottom-up approach, I think chemical vapor deposition is the most commonly employed type of bottom-up approach for synthesis of a graphene. So let's move on to the top-down approach. This is one of the simplest top-down approach that we can adopt for synthesizing graphene. This is what known as the mechanical exfoliation. So there is some adhesive tape. So this adhesive tape we can use over the surface of a graphite, and we can paste the adhesive tape over the surface of a graphite, and we can peel the adhesive tape, and this tape we can then press over the surface of some substrate material, leaving a layer of graphene on that. So this technique we can do many times to make a single layer of a graphene. So this is comparatively very small scale production of a graphene. We cannot use it for a high yield production, and something like we can say like a laboratory approach which we can use for developing graphene. So this is very time consuming process, and we will get only regular shapes and size of the exfoliated flakes, and this is suitable only for laboratory use and it's not suitable for any commercial use. So that are the main pitfalls of mechanical exfoliation using adhesive tapes. Other thing is liquid phase exfoliation of a graphene. This is one prominent technology or a method that we can use for developing graphene. In liquid phase exfoliation, we can use either sonication or we can use some shear forces using some shear mixer to develop the graphene. In the sonication process, actually what is doing is that we'll make some cavity formation, and because of the cavity formation, the force that is generating due to cavity formation helps to detach the layers in the graphite. So we will be using graphite as the precursor material for all top-down approaches because it is like top-down approach, from higher to lower we are making. So graphite will be the precursor material. So for liquid phase exfoliation techniques, it will be a mild, we can use mild operating conditions, and it does not require any high vacuum conditions or does not require any high temperature conditions for making the liquid phase exfoliated graphene. So in case of a sonication method, what we are actually doing is that we will take our precursor material, which is graphite, and we will chop down it into fine powder. And then we can disperse it in suitable solvents like water or NMP or like DMF or THF, whatever it is, and we can disperse it, and we can take it for the sonication process. Once the sonication process starts, what happens is that there develops bubbles in the solution, and these bubbles are very unstable kind, and they will start collapsing. Once they start collapsing, it will produce some kind of force in that material or the solution, and because of that force, the layers will get separated and we will get the graphene layers. So this is a simple probe based sonication instrument which I am shown here. There are mainly two types of a sonicator which we can use. One is the bath sonication process, and the other one is the probe sonication process. In the bath sonication process, we are keeping the solution in a water bath and then providing the ultrasonic power. But in case of probe sonication, what we are doing is that we can insert the probe directly into our solution and perform the sonication process. So this is a mechanism of cavity formation and exfoliation of graphene layers using the sonication process. It's nothing but we are dispersing the graphene in a suitable solvent and we are keeping it for the sonication process. As I discussed, the bubbles will form, the bubbles will enlarge, bubbles will explode, and it will produce a kind of force. And then because of that force, these layers will get separated and we will get separate graphene layers. One another technique is microfluidization technique, which uses high pressure homogenizer. In high pressure homogenizer, some high pressure is exerted to the fluid, and because of that pressure force, the fluid, the solution will get, or the graphitic layers will get separated and promoting the exfoliation. Yet another kind of liquid phase exfoliation is electrochemical exfoliation technique. This is one of the promising method for getting large yield of graphene based dispersions. An electrochemical method is simple, it's efficient, it's somewhat environmental friendly and easily controllable as well. So this will be the total setup of an electrochemical exfoliation process. We require an electrolyte, we require a working electrode, we require a counter electrode for the process to occur. So usually working electrode will be the graphite electrode, because we are using graphite as the precursor material for the graphene synthesis. So our working electrode will be graphite electrode, and the counter electrode will be usually platinum electrode. In some cases, we can use graphite electrode as well, but we highly recommend platinum-based electrodes because this electrode should not get consumed during the process, and it should be somewhat inert as well. So when we are performing the electrolysis process, we need to first arrange the working electrode and the counter electrode, and also we need to take a suitable electrolyte solution. The electrolyte can be some mild acids or some kind of ammonium sulfate solution, something like that. So the electrolyte we can pour into this setup, and we can start doing the exfoliation. Once you start giving the power, you can see that the graphite layers are getting separated. This, the visible change we can see actually after some time. What we can see that the colorless solution will start becoming grayish and then will become blackish, and the small graphite layers will get separated, and the graphene particles as fine powder will get dispersed or deposited in the solution. Later, if we want to do some kind of filtration process or washing process, we can take the solution for filtration, washing and drying process, and we can get the powder form of graphite as well. This is the mechanism of electrochemical exfoliation. The electrolyte will get split up and these ions will get inserted in between the graphene layers. And since the ions are getting inserted between the graphene layers, the distance between the graphene layers increases, and then the graphene layers will get separated out and will get the graphene from the graphite using the electrochemical method. And next one is the arc discharge method. In this arc discharge method also we are using high temperature furnace. It requires some kind of AC welding machine. AC discharge is done in presence of some kind of a buffer gases. And this is not that common method. Usually the exfoliation techniques like electrochemical, other cavitation based exfoliation techniques are most commonly used. And next I am moving to the bottom-up approaches. Bottom-up approaches are comparatively little bit complicated than the top-down approaches because this requires some kind of a sophisticated instruments all, and the conditions should be proper for making the graphene layers. But one of the advantages is that bottom-up approaches can give monolayer or bilayer graphene more like in a regular shape and more with more purity. So generally for chemical vapor deposition, we can use some kind of gases, methane gas or ethane gas. Most commonly methane is using, and carbonization of this kind of gases. Precursor materials are performing over some kind of a substrate materials like copper or nickel, and it will start depositing the carbon layers of the substrates. And it's something like time consuming process, but usually for electrode preparation applications all people are using chemical vapor deposition method, and it's very efficient, controllable, and we can produce in high quantity and high purity graphene using the chemical vapor deposition method. And there are some microwave assisted chemical vapor deposition methods as well for the preparation of graphene using bottom up approaches. And there are some pyrolysis reactions which we can perform for developing graphene. So for this kind of a methods, what we are doing is that we can use some kind of wood box and we can heat it so that carbonization will be performed, and then we can perform some kind of washing process to make the material. So this will be the overall schematic representation how we can do the pyrolysis technique. We can take the wood and then we can perform the hydrothermal treatment of this wood moiety, and once we are doing the hydrothermal treatment it will produce the carbon skeleton, and we can activate this and we can perform some exfoliation, and then we can get the graphene. So this is also one another method but not that common method. Epitaxial growth also is a one type of a bottom up approach, but that also is not that common. In this method silicon carbide wafers are using the silicon carbide wafers. uh, the sublimation, finely controlled sublimation of this material is performing and developing the graphene. One another method is reduction of carbon monoxide. Carbon monoxide reduction using some kind of aluminum sulfide can be performed, and this can produce the graphene sheets. And we can use some kind of organic synthesis methods as well, something like Suzuki polymerization reactions to perform the precursor material. We will use some precursor material, and using some acid treatment we can produce the graphene. And graphene which are produced using the various approaches, they are having wide range of applications in different areas. Mainly because of their conductivity, it can be used for different types of electronic applications. It is having high conductivity, and one another peculiarity is that monolayer graphene will be highly transparent as well because of their conductivity, transparency, and also because of their high mechanical properties and very thin nature. We can use this graphene materials for solar cell applications. Since if it is going beyond one layer, that means if it is going to two layers, bilayers or tri-layers, what is happening is that the transparency of the graphene will get lost. So especially for transparency applications like for solar cell applications or any other electronic applications, we generally prefer single layer graphene materials, and it's because of the transparency we will get at its best at it when it is in the single layer format. So we can use this graphene for different types of electrodes developing, and also for making thin sheets or thin layers or coatings of graphene over the solar cell surface for absorbing light and dissipating the heat energy or thermal energy or the light energy throughout the material. And this is one example of a paper in which carbon dot and graphene based composite material is used for making some kind of a photovoltaic applications. So what they have done is that this is a simple method they have adopted for the device fabrication using graphene. They first took some indium tin oxide or glass substrate layers. On that they developed zinc oxide layers, and then over that they prepared the graphene layers for conductivity applications. So this kind of simple methods are also adopting for developing graphite based or graphene based electrodes or solar cell materials. And since graphene is very lightweight, we can say graphene has a very lightweight, especially when we are going or dealing with the monolayer graphene structures. They are very lightweight, so we can use, since they are very lightweight and they are very flexible as well, we can use it for different types of electronic applications. Like this kind of electronic structures can be developed using the graphene. And graphene also can be used as an adsorbent material for filtration application as well. We know that for water filtration application, we are mainly using activated carbon. So graphene has a higher surface area compared to activated carbon. Because of this higher surface area of graphene can be used for different types of filtration applications as well. And we know that in the graphene structure, there is double bonded structure. So this pi-pi interaction, it can make pi-pi interaction with the organic molecules, and it can selectively absorb organic molecules on its surface, so can be used for water filtration applications. And also graphene has the peculiarity like it's highly hydrophobic, since it doesn't contain any kind of polar functional groups on its structure. Since it is mainly based on only carbon atoms, it is hydrophobic in nature. So because of its hydrophobic nature, we can use graphene, or we can incorporate graphene into other hydrophobic polymer matrix and enhance the hydrophobicity of the polymer matrix and make some super hydrophobic surface using a graphene. So this kind of super hydrophobic surface, since graphene is transparent as well, we can use for a coating over glasses, we can use in vehicles. And also this kind of super hydrophobic surfaces can be, or adsorbent materials can be used for oil water separation. Oil spillage is one of the important problem in seas. So in order to remove the oil from water, we can use this kind of super hydrophobic graphene based adsorbent materials. And there are many other applications also for graphene. People are continuously doing research on how graphene can be implemented for different application. Graphene can be incorporated into polymer matrix or rubber composites in order to provide reinforcement applications, because graphene has pi interactions. Graphene can form pi stacking interaction between the molecules, filler material and the substrate material, and can be making it a highly reinforcing material for a plastic and also for polymers like rubbers, etc. And also one of the important peculiarity of a graphene is that it is highly non-flammable. So we can use it for like non-flammable material fabrications, and also we can use it for developing super hydrophobic, that means waterproof materials. And also we can use it for we can incorporate graphene in concrete materials in order to provide reinforcement. And also graphene has a peculiarity like it can be used for thermal management. It has high heat dissipation capacity, so we can incorporate graphene in concrete or any other kind of materials in order to, or metals, in order to provide heat dissipation capacity. So these are the various applications of a graphene. So when we are comparing graphene and graphite, one thing I can say is that graphene is superior in property compared to graphite, based on its transparency, based on its mechanical properties, based on its conductivity, etc. And then next I'm moving to graphene oxide. This is one another category of a graphene based material. The main difference between graphene and graphene oxide is that graphene oxide contains some kind of polar functional groups on its surface. But in graphene, we saw that it's simply of carbon atom, but here we can see that there are polar functional groups attached to the surface of graphene atoms. So this is like some OH groups or COH groups can be bonded. And the also one another thing what we can observe is that not all carbon atoms are sp2 hybridized. Say for example, this carbon atom if we are taking, it is not sp2 carbonized. So in case of a graphene oxide, when we are comparing with the graphene, we can say that the delocalization or the free movement of electron will be somewhat interrupted in case of graphene oxide, because not all the carbon atoms are sp2 hybridized and the delocalization is somewhat interrupted also. So graphene oxide, one of the most common method of synthesis of graphene oxide is the Hammer's method. This is a very easy method that we can adopt in our laboratories. And in this also, we can use graphite as the precursor material. We will be treating the graphite with the sulfuric acid and then KMnO4 as the oxidizing agent. It will perform the exfoliation and oxidation of the graphitic layers and it will produce graphene oxide. So from graphite, oxidation can produce graphene oxide. Or we can prepare graphene oxide from graphene as well. We can perform oxidation of a graphene to produce a graphene oxide. Graphene oxide also is used as adsorbent material for organic pollutants removal. When we compare graphene and graphene oxide, one thing I can say is that graphene oxide will be having higher adsorption property than graphene, because graphene we know that it contains only the pi electrons. But in case of graphene oxide, there are polar functional groups as well. So these polar functional groups can also interact with the organic pollutant molecules. So pi-pi interaction and also the interaction between the polar functional groups also possible here in case of graphene oxide. So graphene oxide shows superior properties in adsorption kind of application compared to graphene. But electronic, when we are taking the case of electronic applications, graphene will be more prominent or more used for electronic application than graphene oxide. So this is one example what we can use graphene oxide. This is for organic pollutant removal from water. In order to demonstrate the ability of a graphene oxide to remove organic pollutants from water, in this work they have used methylene blue as the organic pollutant. So they have taken a methylene blue solution, incorporated the graphene oxide into the methylene blue solution. What happens is that, as I said, the polar functional groups between the methylene blue and in the graphene oxide interacts, and also the pi-pi interaction occurs. So that makes the material or the dye molecule get adsorbed onto the graphene oxide surface. And what we can see that as the time progress, the dye molecule will get adsorbed onto the surface of this graphene oxide, and there occurs the reduction, and we can see the color change as well. So one of the important peculiarity of graphene oxide is that it can be used for a dye adsorption or organic pollutant removal from water. And this is another dye which is rhodamine B. Same kind of interaction is shown here as well. Graphene oxide can interact with this is some kind of hydrogen bonding interaction which is formed between the polar functional group of rhodamine B and the graphene oxide. And some pi-pi stacking interaction can also be possible. So this is one work in which graphene oxide modified polyacrylonitrile nanofibrous membranes are used for air filtration application and less water filtration application. Graphene oxide can also be used for air filtration applications. As we all know that the air pollution is increasing day by day. For indoor air, for keeping the indoor air quality and also for external air quality, we require some kind of adsorption materials which can absorb the pollutant molecule, especially the particulate matter pollution. So we can make some kind of a sponge materials or membranes that can filter the air particulate matter. Using graphene oxide as the filler material, it can enhance the efficiency of the membrane materials for air filtration applications. So what we can see is that this is one SEM image of the nanofiber which is produced by polyacrylonitrile polymer in which the filler molecule graphene oxide is added. So this is the simple polymer without filler, and this is the SEM image of the polymer with the filler graphene oxide. So this image shows that the polyacrylonitrile itself is not able to provide any air filtration efficiency, or it is not able to trap like particulate matter in its structure. But what we can see is that when graphene oxide is incorporated, you can see that the particulate matter is getting adsorbed or trapped inside the nanofiber layers. This is mainly because of the ability of graphene oxide to interact with the particulate matter and absorb it onto its surface. So this way graphene oxide can also be used for different kind of air filtration applications as well. So when we compare graphene and graphene oxide will be more suitable for adsorption applications like for water filtration or air filtration applications. And when we compare graphene and graphene will be more suitable for electronic applications compared to graphene oxide because of the high delocalization of electrons possible in graphene. And graphene oxide can also be used as a reinforcement material for polymer, rubber, and concrete. Why it is saying? Because as we already discussed, graphene oxide is a material which is having large number of functional groups in its structure. So these functional groups can interact with the substrate molecule and can provide a strong interaction between the substrate molecule, so that reinforcing the material. So graphene oxide can also be used for rubber reinforcement, concrete reinforcement, or polymer reinforcement applications. So this is one of the work in which it is used for cement applications. Graphene oxide and carbon nanotube together they used as the filler material for this application. So they have incorporated the carbon nanotubes and graphene oxide into the cementish material, and they could provide some kind of interaction between the silicate particles and this kind of filler materials, enhancing the mechanical properties. And the presence of large number of functional groups makes graphene oxide as a suitable material for reinforcement application as well. When we are comparing graphene and graphene also is using for reinforcement application. Graphene oxide also is using for the reinforcement application. But in case of a graphene, the reinforcement will be happening by the pi-pi stacking interaction. But in case of graphene oxide, polar functional groups also plays important role. So this kind of materials can be used for reinforcement application as well. Okay. So next about reduced graphene oxide. This is the last category of a graphene based material which I am going to discuss. This is reduced graphene oxide. As the name indicates, this is what the reduced form of a graphene oxide. So you can see like there will be less number of polar functional groups in the reduced graphene oxide. So this is almost similar to graphene structure, but still defects are there. We cannot call it as graphene, but generally people are calling the graphene oxide or graphene or reduced graphene oxide commonly as graphene. But in general, more clearly, if we are speaking, reduced graphene oxide is not actually graphene. It is some kind of defect structure of a graphene. Here also you can see like delocalization is not complete. No continuous delocalization is present. So when we are taking this carbon atom, you can see that it's not sp2 hybridized. And also there will be less number of polar functionalities compared to graphene oxide. So its properties is in between graphene oxide and graphene. Reduced graphene oxide will have properties in between that of graphene oxide and graphene. So reduced graphene oxide, which we can prepare from graphite. Graphite first can undergo oxidation to produce graphene oxide, and graphene oxide can undergo some kind of reduction process using chemicals like hydrazine, and we can produce the reduced graphene oxide. Reduced graphene oxide will be showing the properties more similar that of the graphene, because it is having only very few layers of polar functional groups in its structure. So structure wise also its properties and properties also will be similar to that of graphene oxide and the graphene, because it is coming in between the chemical structure of graphene oxide and graphene. So this also can be used for water filtration application, organic pollutant removal application, electronic applications, and rubber reinforcement or polymer reinforcement applications. This is one of the work which I have done, in which polyurethane, graphene oxide, and titanium dioxide are used as the a material for a dye removal. So what we have done is that we used polyurethane as the main polymer matrix, and we added graphene oxide TiO2 filler material into that. TiO2 means titanium dioxide. Titanium dioxide we have added in order to provide that photocatalytic activity for the polyurethane matrix. Graphene oxide is added for providing that adsorption enhancement or adsorption properties for the polyurethane fibrous membranes. Polyurethane as such, if we are using, we cannot use it for adsorption applications, because it doesn't has any active functional groups which can adsorb organic dye molecules or any other kind of organic molecules. So that's why we have functionalized the polyurethane using graphene oxide and TiO2. What we saw that When we are increasing the concentration of the filler material, it is showing high dye adsorption properties. So quantity of the filler material also plays important role in providing better properties to the polymer systems. This is all about graphene and carbon based nanomaterials. So we discussed about different types of carbon based nanomaterials. We discussed about carbon dots. We discussed about planar carbon based nanomaterials like graphene, graphene oxide, reduced graphene oxide, graphite. And we discussed about the different synthesis methods, its applications, everything. Now I'm moving to another category of material, which is known as MXene. MXenes are also very recently developed kind of nanomaterials, and they are also some kind of two-dimensional nanomaterials. They are actually metal carbides, or we can say it like metal nitrides or metal carbonitrides. So these are like they will have a general formula of the structure MX. So M represents some kind of metals, generally transition metals, and X represents carbide, nitride, or carbonitrides. So these are discovered in 2011. This is the general formula of MXenes. MXenes, where N represents the number of X atoms, that means the carbon or nitrogen or the carbonitride atoms. So this n actually determines the number of layers as well. So generally this will be MXenes will be like 1 to 4 layered. So n plus 1, it can be like 1 to 4 layered. And there are different types of MXenes like titanium carbide. This is one example for MXene. This is vanadium carbide. This is a nitride based MXene. This is vanadium nitride. This is another nitride based MXene. This is titanium nitride. So MXenes also has a general formula like Mn plus 1 xn Tx, especially if they have some terminal groups such as fluorine, oxygen, or OH. This Tx represents some surface terminations. So generally we can say like MXene has this formula where M represents the metal, X represents the carbide, nitride, or TX represents the surface terminations. So I'm going to discuss about this MXene synthesis. Before that, I'll show you what is meant by the total structure of MXene. As you can see, MXenes, this will be, oh, sorry, I'll come to this slide after this. So let's move on to the synthesis of MXene. MXene synthesis is comparatively little bit means time consuming, and it is actually like 1 2 3 kind of 3 steps will be there. Mostly the first step will be synthesis of a layered structure, that is called as the max phase. So in the synthesis of MXene we can see like it is it is a 3-step process, in which the first step is synthesis of a max phase. So that max phase is actually known as the precursor material for the MXene synthesis. So this max represents MAX, where M is the transition metal. A means it is a kind that also is a kind of transition metal. X is a carbide metal. So in MXene, layered MXene precursor synthesis is first done, and the max phase is forming. Max phase is actually MAXN. So this is the general formula of the max phase. The max phase contains material or atom which is A. A is actually a transition metal which comes in between group 11 and group 16 of the periodic table. Once the max phase is formed, this A layer is etched using some kind of organic chemicals, and that is forming the multi-layer MXene sheets. Once the multi-layer MXene sheets are produced, delamination of the multi-layer sheets are performed and producing single to few layers of MXene sheets. This is the overall synthesis procedure for the MXenes. So we will be first making the max phase and then etching of the A atoms from the max phase, and then delamination of the multi-layer MXene into MXene. So this is the synthesis route which I can show like schematic representation. So this is something like MXene structure. So M dash double dash, these are like metals, and A is the another metal, X is carbide or nitride. So this will be the general structure of the max phase. generally, like the metal will be there, it will be bonded with the X atoms, and this will be the A atoms. So there are different types of a max phase possible, like mono M or multi M. Multi M, in this case, there will be two types of metal atoms in that. And this multi phase or this max phase is first formed. And after the max phase is formed, this A layer is removed. So this the A layer is removed using some kind of hydrofluoric acid kind of acids, and the A layer is removed from that using acid treatment, that means etching treatment, and the A layer is removed and it is forming multi-layer MXene structure. From this a multi-layer MXene structure, delamination of the multi-layer MXene structure is performing and producing the single layer or double layer of MXene sheets. So this will be the general. To understand what is max phase, I have kept the picture of a periodic table where this atoms all comes. So generally the metal atom will come in the range like from 3 to 4, 5, 6, 7 atoms in the period group. And in case of these A atoms, they will generally come between this elements in the periodic table, and this is the carbide and nitride which is shown in red. So this will be the general structure of max phase. And MXenes, they have high mechanical flexibility, they have high hydrophilicity, and they have high conductivity as well. When we take the case of graphene or graphene oxide, reduced graphene oxide, when we talk about the hydrophilicity of those materials, we can say like graphene is hydrophobic in nature. Graphene oxide, since it contains polar functional groups, it is hydrophilic in nature. And reduced graphene oxide, which is having property in between that of graphene oxide and graphene, so that we can say like it is more hydrophilic than graphene but less hydrophobic than graphene oxide. Less hydrophilic than graphene oxide and more hydrophilic than graphene. But in case of MXene, they are highly hydrophilic. We can make the water dispersions of MXene so that we can use it for some kind of ink making, like conductive ink making applications, because graphene oxide, MXene can be easily dispersed in water. And also it is having high mechanical flexibility so that it can be used for flexible supercapacitor making applications. And also MXenes are conductive, because of that it can be used for electrode ink, that means conductive ink fabrication applications also. So these all about MXenes. Now I have finished all the I tried to give you an outline about the different types of graphene based, MXene based nanostructured materials. Now I am moving to self healing materials. This is another category of functional materials which is found in the uh, material science applications. Self healing materials are a kind of materials which can repair itself when the object is damaged up to an accepted or considerable level of damage. We are not saying like it can withstand all the force, but up to an level it can withstand force. So self-healing materials are those kind of materials which can repair by itself, or we can call it as some kind of a smart materials that can withstand environmental stress, that includes oxidation, radiation abrasion or impact, or thermal decomposition or moisture. So I'll be discussing about the self-healing materials. So when we take the case of nature, what we can see that the nature also is having some self-healing capacity. When we take the case of our normal skin, what if some cut is formed over our skin, what we can see is that within few days the cut will be recovered, or the skin will get regenerated, even if we are not applying any medicines. Uh, Even if we are not applying any medicines also, the cut will get regenerated within few days, especially like if it is small cuts, will get regenerated within some 14-28 days. So that is a normal kind of natural mechanism for self healing for our body. And some feathers, chameleon, these all are the natural self heal examples for natural self healing properties. Similarly, researchers are trying to mimic the self healing properties or self healing properties of nature in order to make some functional materials. So this is another self-healing property of a lotus leaf. As you can know, as we all know that lotus leaf, when we are pouring water over the lotus leaf, it won't get wet by its surface. It's mainly because lotus leaf surface has some kind of micro nanostructures on it, which will help the water molecule to roll off from the surface. So it's all about the surface characteristics of the material, which is actually making the ability to withstand or resist the moisture of water. So similar way, self-healing materials we can prepare in our laboratory as well. And the self-healing mechanism, it can be of a physical or chemical. Physical mechanism involves some shape memory effects or some interchain diffusion or phase separator morphologies. And chemical mechanism occurs through some dynamic bond formations like covalent bond formation, free radical or supramolecular interactions, or we can club this physical and chemical mechanism together to produce some physico-chemical approaches for self-healing mechanism. So this figure represents some kind of mechanism of self-healing of materials. In the first one, we can see that it is something like some nanoparticles we can incorporate in the materials, so that this nanoparticle can act as the healing agent and can recover its shape, and some phase separated morphologies, and some shape memory recovery. This is some shape memory applications of or mechanism of self-healing ability of the materials. And melting interdiffusion, using some heat energy we can melt the material and interdiffuse between the material, or we can use some kind of physico-chemical approaches like van der Waal interaction and also phase separation together, and some chemical approaches like we can incorporate some kind of functional groups on the material, so that when they got cut or damaged, they can recover together by forming covalent bonding or free radical rebonding or hydrogen bonding or pi-pi stacking or guest host chemistry or metal ligand coordination or ionic interactions. So importance of, now I'm going to talk about the importance of nanoparticles in self-healing. Nanomaterials can enhance the effectiveness of external stimuli for self-healing applications. As we already discussed, there are many applications for nanomaterials. We can use it for different types of drug delivery applications. We can use it for some nanomaterials can be used as drug molecules. Nanomaterials can be used as carrier molecules for a drug targeted delivery. All nanomaterials can be used as antibacterial agents. As I discussed, silver nanoparticles, it is having high antibacterial activity. Even gold nanoparticles also possess antibacterial activity. So we can use it for antibacterial applications. And nanomaterials can be used for electronic applications. Similarly, nanomaterials can also be used for self-healing applications. Nanoparticles can be used as a self-healing agent as well. So, nanoparticles can actually provide the activation energy required to establish covalent bonds or intermolecular contacts between the cut surfaces using with the help of some external stimuli like heat, light, or magnetic field. So, this is one work in which silver nanoparticle and some polymer is used. So this one represents a self-healing material which is prepared using a polymer which is NIPAM. NIPAM means an isopropyl acrylamide. It is a polymer which is having high temperature stimuli responsive nature. So NIPAM is a polymer which is having high temperature stimuli responsive nature. So when we are trying to make some kind of material using NIPAM, that material will have the ability to absorb heat energy and to self-heal by itself. So in this, they have added silver nanoparticle as well, and they prepared the polymer material. And this polymer material, they cut into two pieces, and the silver, since silver nanoparticles are incorporated in this material, silver nanoparticle has the ability to provide the required energy to bond these materials together. So what they have done is that they first prepare the polymer based self-healing material using NIPAM polymer and silver nanoparticle as the curing agent, and then they applied some laser radiation in between this cut edges, and within 1 minute they could observe that this material shown the self-healing property, that the material joined together. And this is the material after stretching, after the healing process. So what they have seen is that silver nanoparticle can provide the healing or make the healing process faster. So they could see that within 1 minute the material undergone the healing process and regenerated its normal shape. So nanoparticles and nanowires made up of metals such as gold and silver have shown remarkable heating properties when exposed to laser light. To further improve the effectiveness of laser radiation in healing polymers, we can use this kind of nanomaterials. So this nanomaterial can provide the required energy to provide the healing process. This is one another work in which microcapsule based self healing materials are used for concrete applications. So microcapsules are those kind of structures which is having some shell structure, and inside the shell structure there will be some kind of a healing agent. So this microcapsules can be inserted or incorporated in the cementitious material, and when some cracks or damage is happening, this microcapsules also will get cracked or open up, and this self-healing agents from the microcapsule move towards the crack area, and then what happens is that this help to heal the material. So this is one example of cementitious material in which microcapsules are added. Healing agent is encapsulated in the form of microcapsule to the cementitious material. The capsule breaks when the cracks or damage occurs, and the released healing agent flows heal these cracks. So this kind of nanomaterial can be used as a microcapsule or healing agent for concrete applications as well. So this figure which I have represented here is the self-healing asphalt applied in Fenkai Road, Shanghai, China. So people are using this type of healing agents or self-healing materials in cementitious materials for this kind of transport applications. So microcapsules means it will be having some kind of shell morphology in which some kind of healing agents will be added in that. So shell morphology or shell structure can be prepared using different types of polymers, and we can encapsulate the functional healing agents in that. And for this particular application, they have used the or they prepared the shell using urea formaldehyde resin, and the healing agent they used was some epoxy resin which is E51 based. So these are some applications of a self-healing agents, how nanoparticles take part in self-healing process, everything. And this is one another example for self-healing material. This is a self-healing rubber. We now discussed about the self-healing polymers, self-healing cementitious material, and now we are going to discuss about the self-healing rubber material. So in this work, what they have done is that they prepared a photo-cross linkable and self-healing elastomer by compounding polybutadiene rubber with the liquid polysulfide. And the disulfide metathesis occurs here. It's kind of a chemical rebonding which is happening here. A chemical rebonding disulfide metathesis using free radical mechanism. So in this polybutadiene rubber undergoes a self-healing process in the presence of UV radiation, and they get healed and producing material with the self-healing properties. So this is one another example. We can make self-healing rubbers as well, self-healing polymers, self-healing cementitious materials, etc. And this is one another work which is done by me, in which this is another category of a self-healing materials. So self-healing materials, there are some materials which can withstand fouling nature. That means if we are preparing some coating materials or membranes, especially for some coating applications, like for coating over the glass surface or coating over the vehicles, what we can say is that mostly people are trying to make coating materials which are liquid resistant, like water resistant or oil resistant or some other liquid resistance, to enhance the properties of a coating materials. So what we have done is that we prepared a membrane material using polyurethane polymer and reduced graphene oxide and molybdenum sulfide as the filler materials. So as I discussed, reduced graphene oxide, it is having a hydrophilicity lesser than graphene oxide, and higher than graphene. So reduced graphene oxide can also be used for making some kind of a super hydrophobic surface. So polyurethane is a hydrophobic polymer. When we have incorporated reduced graphene oxide and molybdenum sulfide into the polyurethane matrix, what happened is that it helped to increase the hydrophobicity of the polyurethane matrix, and it made some kind of a super hydrophobic surface. So when this polymer, when we try to dip it in the water solution, or and what we have seen is that this material is not getting wet by water. So this is something like a muddy water which we have shown here. This mud water, if we are putting this membrane in the mud water and if we take out the membrane, what we can see is that this membrane has it's a surface has the property like to self heal. That means the membrane will not get wet by water and will not get wet by any dirt particles. So this kind of membrane materials we can make using functional nanomaterials in order to make the surface water repellent or any liquid repellent. Any liquid repellent surfaces means they are known as omniphobic surfaces. Omniphobic surfaces, super hydrophobic, if we are saying it will have ability to repel water only, but in that case those material will get wet by oil particles or any other organic solvent particles, etc., or solvents, etc. But in case of when we are trying to make omniphobic surface, what happens is that omniphobic surface can withstand all type of liquids, many range of liquids it can withstand, like it can withstand water and it can withstand oil as well. So in this figure you can see that it is getting repelled by water. So when we are dropping water over the membrane surface, what you can see that the water will get rolled off like beads, like how lotus leaf behaves when with water. So functional materials or nanomaterials we can use for different types of applications. It can be used as filler material for enhancing the properties of the parent material, especially if we are taking the case of a polymer material. A wide range of research is happening in case of like functionalizing the polymer materials using nanomaterials. One important peculiarity of using nanomaterial is that we just want to give only very less quantity of nanomaterials into the polymer matrix or to the substrate matrix so that it can give a very high property enhancement. As what we can see here is polyurethane. If you are simply taking the polyurethane and putting it in water, you can see that it is getting wet by water. Even though it is hydrophobic, it will of course little bit it will get by water. And if you keep the polyurethane membrane as such for a long time, you can see that it can show fouling as well. That means fouling layers can form over the membrane surface. But if we are using some kind of nanomaterials in that as a filler material like graphene oxide, what I said, is actually enhancing the surface property of the materials. So it is providing some kind of additional property to the membrane materials. So in this way, we can use nanomaterials for different types of applications. And this is an emerging field and many research is going on in this field. Day by day, different types of new materials are fabricating, new applications are coming, and it's like an emerging field of chemistry, or it's something we can say like as an interdisciplinary field which has applications in material science, nanotechnology, polymer chemistry, biomedical science, etc., etc. So that this is one another self-healing material which is formed formed by some kind of covalent bonding interactions. So this just represents the mechanism how it is getting bonded. So this is something like a polymer, PVA based polymer in which borax is added. So when this polymer get cut and when we are trying to heal it using some UV radiation, what happens is that the functional groups present in the molecule get attached to this molecule and providing that strong interaction between the two cut edges and making the material to get self-heal. And after the self-healing, this materials, it can we can stretch the molecule and it can able to withstand the damage to an extent. So this is all about the self-healing materials and all about the nanomaterials, everything. Hope this discussion helped you to get some knowledge. Thank you. Thank you.
Yeah, thank you, ma'am. Now the forum is open for the discussions. If any participants have any questions, you can ask Sagitha ma'am. Anyone is having any questions? Yeah, I'll unmute first. Yeah, any questions? Yeah, Vinay, already you have been unmuted. You can ask the question instead of typing in the chat box.
Yeah, I saw that question. Graphene for food packaging applications. Okay, fine. So food packaging applications, we are mainly using in our present industry, we are using polymer-based material for food packaging applications. But one of the major problem with this kind of food packaging materials that we are preparing is mainly because of polymer-based systems that we are using. But as we know, the use of polymers or plastic materials are increasing day by day. It is getting dumped into our nature. So people are trying to develop some kind of a packaging materials which is biodegradable and which should not make any issues to the environment. So in that case, researchers are trying to develop a new kind of a paper based or any biodegradable material based packaging materials. So if you are taking some paper based material for making packaging applications or packaging materials, paper itself won't be able to give all the properties required for the packaging application. So we will have to do some kind of functionalization into the paper material to make it hydrophobic and also to give some mechanical properties, etc. Of course, we can use some kind of functional filler materials like nanomaterials in order to make it super hydrophobic or in order to provide that mechanical strength, etc. We can use graphene also for paper plastic making applications. But one of the peculiarity that we will have to keep in mind, especially if we are using for some food packaging application, we will have to think about the toxicity of the material that we are using as the functional fillers. So graphene is not that biocompatible. Even if it is biocompatible, it is a naturally derived material. Of course, everything is okay, but especially for food packaging application, when we are thinking, we will have to think about the cytotoxicity of the graphene material that we are using, because this filler material of course will come in contact with the food material. And any other applications like for packaging of any other electronic gadgets or something, we can think of graphene based materials, because graphene based food packaging materials have one important peculiarity is that it can be used as a flame retardant material, especially for those kind of materials which are highly flammable. Though for making those kind of packaging, so for transporting flammable materials, we can use graphene as the filler material for the packaging applications, because graphene will make the packaging material flame retardant. So that is one advantages of using graphene as one of the packaging material. One another thing I can say, like when we are incorporating graphene in the packaging material, it can actually enhance the mechanical properties of the packaging material, so that it can give mechanical stability, some strength to the packaging material. And also one another thing which I can say is that when we are incorporating graphene to the packaging material, it can actually increase the surface hydrophobicity of the packaging materials. So that also we can say. And also one other peculiarity is like heat dissipation capacity. So it can actually dissipate heat. It won't make the material to get heat to get won't get accumulated if we are homogeneously dispersing graphene on over the packaging material surface. So these are some advantages that we can use when we are using graphene as a packaging material for graphene is using as a filler material for packaging applications.
Hello, ma'am.
Yeah.
Good afternoon, ma'am.
Good
Um,
afternoon.
Ma'am, if I want to go for manufacturing a composite material
Yeah.
and I want to strengthen, say, for example, any base material with graphene nanoparticles, and
Hmm.
there may be one option of use of graphite. So,
Graph.
ma'am, would you please tell us about the use of either we can go for a multi-walled carbon nanoparticles like graphene or graphite, because when we go for any kind of mixing or milling procedure, that may deform the shape of nanoparticles. But on the other hand, if we go for any graphite kind of particles, so ma'am, would you please tell us about the query?
So this is about using graphene as the filler material for composite preparation, right? Okay.
Well, it is addition of like preparation of composite, not filler material.
Okay.
You can say the strengthening material.
Okay, fine. So composite, as we all know, it's a kind of material in which a polymer and some kind of inorganic material will be like incorporated together to enhance the property of the parent material. So
Ma'am,
we
it is like MMC, metal matrix composite.
metal. Okay, fine. So graphene, as I explained, we can use it for composite preparation. But one main important thing is that when we are trying to make any composite materials using graphene, the dispersibility or the homogeneous dispersion of the graphene in the material is very important. So when we are taking graphene, it should, especially for composite preparation, if you are doing some melting process or some kind of a grinding or ball milling process, whatever it is, the material should go homogeneously distributed over all the metrics. Otherwise it will not give the required properties. Like if it is getting aggregated on one corner, it will give some property at that particular corner, and at the other corner it will give some different properties. So homogeneous distribution is always important. So as for those kind of application, we can use a graphene based powder for composite preparation. Fine powder we can use. I didn't get the question about multi-volt carbon nanotube which you have asked. So
Ma'am, actually, I was asking about if we go for preparation of any metal matrix composite, and we in that we will reinforcing the material with like graphene.
mm,
Uh, will it change the shape or any agglomeration kind of problem will be there? Or if is there any method to homogeneously distribute the reinforcing agent without disturbing the shape or deforming the shape of particular material?
okay. Could you please tell me which method you are adopting for the distribution or the composite preparation? Like, is it like a ball milling process, or is it like,
Certainly, certainly.
sorry, ball milling?
But yeah, yeah.
Okay, ball milling process we can use for a mixing or a composite preparation with the graphene. It's an efficient method. It won't give any molecular level disruption to graphene. It's like we'll get chopped down the graphene material, but it won't give any molecular level disruption to graphene. And when we are going for ball milling process, in order to enhance the homogeneous mixing of the material, it's better to go for a higher temperature, higher time mixing, longer time mixing. So if you go for only 5 minute mixing, and if you go for some 5 hours mixing, there will be difference. Of course difference will be there in the homogeneous mixing. It's better always go for optimization of the time, how long you will have to perform the mixing, and what rpm you should perform for the mixing process. Everything you will have to optimize. And if we are going for some solution based mixing process, first we will have to go for making the dispersion of the graphene. This dispersion, rather than making the dispersion using normal magnetic stirrer, it is better to go for sonication based process for making the better dispersion, because sonication can enhance the dispersibility of the material. It can form stable dispersion. After making the stable dispersion, you can incorporate into the matrix material. But especially for metal application, ball milling will be the most appropriate method for dispersing the material. And ball milling will not cause any kind of molecular level interruptions to the material. Some kind of small defects may occur, but still may not. And another thing is that when we are doing ball milling process, some kind of polar functional groups, some impurities can also come into the structure. Homogeneous distribution, of course, will be possible with the ball milling process if we are using highly dispersible kind of a graphene material. There are different types of different grades of graphene materials: flake like graphene, powder like graphene. I will say like we can go for a powder like graphene material for getting the better dispersion, homogeneous dispersion for metal kind of applications, rather than when we go for flake like materials.
Okay. Thank you so much, ma'am.
Thank you.
Hello, ma'am.
Yeah, hello.
Ma'am, myself Prashant from JIT College, ma'am.
Okay,
Ma'am, while accelerating self-healing processes,
okay.
how the stimulating like using heat or electricity
Yeah, we can
from
stimulate it
temperature
using
what?
heat or electricity, or like we can stimulate using some laser radiations. So it is like self-healing materials. If I'm taking the case of a nipalm is an isopropyl acrylamide. It's a polymer which is having high temperature stimuli responsive characteristics. So especially if you are trying to make some kind of a self-healing materials, based upon the application, you will have to select the polymer. And if you are looking for some thermal healing agents, you can use this kind of heat responsive or temperature responsive polymers like nipalm. So these polymers, when you make the self-healing material, and if you cut the material into two pieces, and if you try to join them by keeping them together, and if you are giving some kind of heat energy or thermal energy at the cut edges, it can actually, using that temperature, some molecular level interaction will happen between this polymer cut edges. The bonds will get cured. That means some kind of bonding interaction will happen between the structures of these molecules, functional groups, everything, and it will get cured. So you can use light energy as well, like you have UV radiation we can use, and we can use laser. Just we need to splash laser over the surface of the cut edges, and in order to make the healing process more efficient and to happen it in very less time, we can add some self-healing agents into the polymer matrix. As I said, we can use some nanomaterials into the polymer matrix so that it can enhance the self-healing properties.
Okay, ma'am. Thank you.
Thank you.
Yes. Any more questions? I think if any more questions are there, we will put the email ID, or you can contact or email our today's speaker, Sagitha madam.
Yeah, sure, of course.
Answer. Okay, so because now it's the time for the next session, and it's from Professor Kapil Gupta from University of Johannesburg. So before that, I think we'll take 5 minutes break. Yeah, for 5 minutes break, and we'll start sharp at 3:50. 3:50. Yes.
Thank you everyone. Thank you for listening.
Thanks a lot for a very wonderful session, and the contents were very good. So here in the coordinators room also, where everyone has appreciated. Thanks a
Thank
lot.
you.
Thanks a lot.
Thank you very much. Thank you.